Hello and welcome to another tutorial. In this tutorial I'm going to continue the discussion on root finding algorithms. So far we looked into algorithms based on just bracketing the roots and looking at the sign of the function at the two endpoints. But now we're going one step further and look at the methods that take advantage of the other informations that the function can provide. So one of the methods is Brandt's method, and this is I took this part from Wikipedia. And in Wikipedia, if you just search for Brandt's method, it takes you to this page, and what you read is something like this. In numerical analysis, Brandt's method is a root finding algorithm combining the bisection method, the secant method, and inverse quadratic interpolation. So far we've seen bisection. We will look at the secant method and then the inverse quadratic interpolation. It has the reliability of bisection, but it can be as quick as some of the less reliable methods. The algorithm tries to use the potentially fast converging secant method or inverse quadratic interpolation if possible, but it falls back to the more robust bisection method if necessary. Now this means that you check the conditions of the function, and if you cannot apply the quadratic interpolation or the secant, you just go and do the bisection. Brandt's method is due to Richard Brandt and builds on an earlier algorithm by Theodorus Decker. Consequently, the method is also known as the Brandt-Decker method. So I'd seen some softwares like MATLAB, you might see Decker method instead of Brandt's method, so that's another name, Brandt-Decker or Brandt-Decker method. Now before we go into Brandt method, let's first check out the secant method. Now here I plot a function f of x, and let's assume that we start with an initial interval which brackets the root. Bracketing means we already know that the root has to be in this interval, or the function has at least one root in this interval. And the way we check for that is just by making sure the function actually changes sign when it goes from the beginning of the interval to the end of the interval. Okay. And so this is the secant method that we're trying to look at first, and then we're going to search for the roots, let's say in the initial interval of x0, x1. This is also called quasi-Newton method, and I'll explain later why this is called the quasi-Newton method. Now, as you probably guess, just like the bisection or trisection, we are going to implement a recursion for this algorithm for secant method. And the algorithm is like this. So we start with the 2 points that bracket the root, and then find the value of the function at these points and draw a line from the beginning to the end, and then find the point that this line crosses the horizontal axis, and most likely this point, as is shown here, is closer to the root than the original points. Okay, and then we take the x1 here and x2, which is the crossing point, and then do the same method. So from x1 to x2 we draw the line and continue to find where it crosses the horizontal axis, and then we repeat that for x2 and x3. So x3 here, x2, draw a line, and then see where it crosses the horizontal axis, and this sequence hopefully converges to the root. And in most cases the convergence is faster than the bisection or trisection method. So in terms of recursion, let's say instead of having the x0, x1, we have the last two terms, last two approximations, xn minus 2 and xn minus 1, and then the values here are f of xn minus 2, the value of the function, and here is f of xn minus 1. Okay, So the slope of this line is f. So actually here I have the equation for this line. The slope is fx f x n minus 1 minus f x minus n minus 2 divided by x n minus 1 minus x n minus 2. So this is the line, okay, the slope. And then the line crosses x n minus 1 and f of x n minus 1. So using the slope and this one point, we can find the equation. And now if I want to find xn, I set the y to 0 and solve for x, because that's the point where this line crosses the horizontal axis, okay? So x becomes xn minus 1, we take it to the other side, minus xn minus 1 minus xn minus 2 divided by the values of the function, alright? So this is the secant method, and definitely we're going to use recursion to implement it. Let's head to Eclipse and implement the secant method. So in our demo root project, in the real root, we have bisection. Let's copy the bisection here. And bisection with initial guess. We have bisection that returns a list of roots. We have trisection. We have a trisection that returns a list of roots. And now we're going to implement the secant. And we only need 2 points, start and end. And let's remove the initial guess, and the stop condition is that start plus n half. So either a start of the interval after some iteration is the root, or end, or the length of the interval is very small, so we take the midpoint of the interval as the approximation. And now we're going to implement secant method, and the way we're going to implement is like this. So I'm going to call it x1, which is the start point, and y1, which is func.value at x1, okay? And then double x2 and y2 is func.value at x2, and double x3. Eventually x3 is x2 minus y2 times the coefficient, and this coefficient was inverse of the slope. Coef is x2 minus x1 divided by y2 minus y1. So I'm going to comment it. Coef here is the inverse of the slope of the secant line, okay? Coef. So x3, and then we're going to set the root to basically secant. Now the recursion. So how do we do the recursion? We assign the root to secant of x2 and x3, okay? So x1, x2 is the original start point, and then we find the new crossing point from the horizontal axis, x3, and then we go into x2, x3, and hopefully this converges. Let's go and test it. We're going to here, test, and public is, let's just copy the first one. We're going to do test 7, and x times x squared minus 2. We have the function. We're going to search for the root using the secant method, and let's say minus 2 to 5, and the actual root is plus minus a square root of 2. So let's see. So it returns minus a square root of 2. If I set it to 0, it returns plus a square root of 2. And it's relatively fast. In order to see how fast it is, let's see how many, let's look at the steps. So I just do a system out print line on the x3. Okay, and then let's just remove this one. All right, 1 2 3 4 5 6 7 8 9 10. Basically 10 steps it converges. So it starts from 0.4 and then 0.74 and then 2, 1.267, 1.387, 1.415, 414, and it basically converges. So the convergence is relatively fast. Let's return this one. Okay. Yes, this was the secant method, and we can implement exactly the same thing that we did here for the secant to return a list of all roots, trisection, secant, sub-intervals, everything is exactly the same, and we're going to invoke the secant method here. And again, this way of implementing the recursion makes life much easier when we're trying to adapt this method to any type of algorithm. So I'm going to have test 8 here. Func here, let's call this root finder, and then a list of whatever roots. It should be double, but we can also use a wildcard. I'm going to use a wildcard, which is actually not recommended, but let's use it. Roots equals root finder secant start minus 10, 10, 100 intervals, and it prints the root. We're going to invoke test. So this should be test 8, and let's invoke test 8. As you can see, there are some duplicates that happen, and that's because of the accuracy of the double. So these are all minus square root of to square root of, but with different accuracies. So instead of using the root contains math.abs of let's change it to the potential root. So we know that the potential root, we can add another if to check the accuracy. So basically we should check this one with all the roots inside, and if the difference is less than the absolute error, we should assume that it's the same. And right now the accuracy here is not exactly the same, but these numbers are pretty much the same numerically. That's why it returns more roots than we actually have. So what we can do is that if it's not nan, we're going to check another maybe have a boolean here, repeated is false, and then for int I equals maybe j equals 0, j less than roots dot size j plus plus. If math.abs potential root minus roots get j is less than absolute error, then repeated is true, and then if not repeated, add the root to the. Okay, now it works. So we're using secant method over some interval, let's say minus 2 to 10, for example. This should return only 2 roots, okay. Minus 1 to 10, this should return 2 roots, 0 and 10. This returns only 1 root. Minus 5, for example, returns 2 roots. All right, so this is the secant method. And now if we head back to the Eclipse and go to actually to see what the Brent method is. Now Brent method is exactly similar to the secant method, but instead of having a linear interpolation fitting a line, we do a quadratic interpolation. So a second degree polynomial instead of a first degree polynomial. But in order to do a second degree polynomial interpolation, we need an extra point, right? We need 3 points to fit a second degree polynomial or a quadratic polynomial, okay? So the assumption is that the root has been already bracketed, which means we already know that in the interval of x1, x2, we definitely have at least 1 root. And then we start with an initial guess, x3, and then use these points x1, x2, x3. Use the y values. So y1 is f of x1, y2 is f of x2, and y3 is f of x3. And we do a quadratic interpolation. And this format of quadratic interpolation is very easy to remember, and that's called the Lagrange interpolating polynomial. So basically the idea here is that you take y1, y2, y3, and the polynomial, it should return the value x1 when you substitute y with y1. It should return x2 when you substitute y with y2. And in order to do that, we have x1, x2, x3 with some coefficients. And the coefficients are, for example, for x1, the coefficient is the 2 other indices, y minus y2, y minus y3, y1 minus y2, y1 minus y3. Okay, so here I, j, k run from 1, 2 to 3, and I and j and k are different. So we have 3 combinations of pairs, right? 1, 2, 1, 3, and 2, 3 for I and j. And then k is also the 3rd index. So for example, the coefficients of x2 is y minus y1, y minus y3, y2 minus y1, y2 minus y3, okay? So we do this quadratic interpolation of these 3 points for the y values, and then exactly like the secant method, we find where it crosses the horizontal axis, and hopefully it's closer to the root than the previous points. So if you set y to 0 here, you get yi, yj, yk minus yi, yk minus yj times xk, okay? And we had x1, x2, x3, and then this one is the new point, x4, and then we do the recursion with x2, x3, and x4, okay? So this is the idea, and obviously you can see that we can increase the order more and more. So instead of quadratic, we can start with 4 points and do a 3rd order polynomial, but there's really no need for that. So let's head to Eclipse and try to implement Brent's method. Let's go to real root. So I'm going to copy the secant method here and change it to Brent. And for Brent, basically we need the initial guess 2, and then the stop condition is still the same. If after some iterations the interval is small, so if the start point is the root, we return it. If the end point is the root, we return it. If the length of the interval is very small, then we return the midpoint. Now implementing Brent's method. Okay, exactly the same thing. x1 is start, and then y1 is func at x1, x2 is end, y2 is func at value x2, x3 is guess, and y3 is func at guess. Okay, and then eventually we want to have x4, which is coef1 times x1 plus coef, these are the interpolation coefficients, x2 plus coef3 times x3 after replacing the y with 0. So coef1 is the coefficient of x1, so we should use y2 y3. So y2 times y3 divided by y1 minus y2 times y1 minus y3, and then double coef2, we should use y1 and y3. y1 times y3, y2 minus y1, y2 minus y3, and then double coef3, we should use y1 and y2. y1 times y2 divided by y3 minus y1, y3 minus y2. Okay, and we find x4, and then we run the Brent for the recursion. We run Brent on x2, x3 and x4, and in order to check the convergence, I just do a sysout on the x4. Okay, then x4 is the new crossing point. Crossing point with the horizontal axis. This is where y equals 0, the polynomial, the interpolation. Alright, let's go to the test. Let's copy this. Test 9. I'm going to run test 9, and then we're going to call the Brent on the 0 to 5 with the initial guess of 1, for example. And let's first comment this. So 1 2 3 4 5 6 7. See, after 4 steps it already has a 3 or 4 digits 3 digits convergence, 3 decimal point accuracy, so it's pretty fast. If you recall, secant you required I believe 10 steps. Okay, I removed the print value of the secant method. Okay, let's comment this and test 9. So Brent is relatively faster than secant, but we didn't check for one specific condition. If any of these fails, y1 equals y2 or y1 equals y3 or y2 equals y3, then these numbers are not a real number, it becomes infinity. So we have to check for that. And to see that, let's say here x squared minus 2 is an even function. So if I put minus 5 to 5, right at the first step it fails because it cannot calculate the coefficients, so it should return a NaN. Yes, so we run into error because it cannot convert because it returns a NaN. But if I change it to anything else, it should be fine. Yes. Alright, you just have to be careful for that, and that's why in the Wikipedia, if you recall, it says that the algorithm tries to use the potentially fast converging secant method or inverse quadratic interpolation if possible, but it falls back to the more robust bisection method if necessary. So if somehow the quadratic interpolation fails, we can program it to fall back to the secant method, and if the secant fails, we can program it to fall back to bisection method. Obviously I didn't do it here in the code, I just directly implemented the Brent's method. but you can, as a practice or as an exercise, you can try to check these coefficients and try to fall back. For example, let's see what happens if we divide by 2 over 0, for example, a double 0, infinity. So it either returns infinity or a nan, not a number, and we can check for that, and if it fails we can fall back to the secant. Now obviously I can also have a method for the Brent that returns a list of roots with the subintervals, but first I'm going to also create a method for Brent that doesn't have an initial guess, and you can probably guess how I'm going to do that. I'm using the method overloading. So in the first step we just manually define a guess, start plus end, the midpoint, and then we call the previous Brent method. Okay, so this just assumes that the initial guess is the midpoint in the middle of the interval and everything is the same. And then we have the Brent. Instead of secant, I call the Brent and use this method that only takes 2 points without initial guess. And this shouldn't be integer now, this should be a double. And in order to check for that, I'm going to use this. This is test 10. And again, I'm using the wildcard here and call the Brent method with an integer, and we're going to invoke test 10 minus square root of 2 square root of 2. And let's say we have x times math.sin of x. We have a lot of roots, but the problem is that some of them are duplicates. Let's see, 2.76 e minus 8, 1.95 e minus 8, these are all 0, and that's why it's failing to recognize that. So maybe instead of having this absolute error when it goes to 0, let's say e minus, I don't know, 7 or something like that. Nine, 6, 12 minus 9, 15. And we can also check by just plotting the function. And as you can see, from minus 5 to 10, from minus 5 to 10, we have one at 0, we have here, and so the problem here is that there are some roots that are outside. Mine 15, minus 9, 12, 6. One, 2, 3, 4, 5. So there's definitely some problem here. 34. We can also maybe plot minus 50 to 50, because there are some roots apparently outside the interval. And then let's look at the 43. So there is one root here, 4398, so it's 44, so that's correct. And there is one root at 2 here, 2.18. Okay, no, 2.18 e minus 8. So this is basically 0, which is correct. We have a root at 0. And then minus 6.28, which is minus 2 pi, and that's 0. Minus 3.14, it's minus pi, it's 0. Plus pi, minus 34. So minus 34. 0.55. $34.55, yes. So the roots are correct. The problem here is that they are not all of them are in the interval that we want them to be, and that's very bad. And that's because of the way the secant works. So for example, if I, instead of the Brent, I call trisection, I get 1, 2, 3, 4, 5. Exactly 1, 2, 3, 4, 5. So I'll leave it as a homework to you to try to modify the code for the Brent method, the one that returns all the roots, to make sure that only the roots that are in the interval are returned. And that's very easy, right? So you check for these, and all right, let's just add it. You don't need to practice on this, so I can do it for you. And then basically start is less than or equal to the potential root, and potential root is less than or equal to end. Now if I call the Brent again, which returns a list, hopefully this time we end up with yes, 2 pi. Okay, there is one that is 9.42, which is here. 1, 2, 3, 4, 5 roots. So the first one, 2.8 in 10 to the negative 8, this is 0. And then minus pi, pi, and then 2 pi, and then 3 pi. So now I'm just limiting the result to the interval. But as you can see, you have to check for that, and the Brent, if without this, it actually returns other roots that are outside the interval. That's because this line could actually go farther away, and then when you do the continue the secant or the Brent with the quadratic polynomial, you can end up with the other roots if the function has more than roots, because yeah, this point could end up outside the initial interval. Alright, so far we have the bisection, trisection, secant, and Brent method, and next we're going to look at other methods such as Newton and see how they actually work. Thank you for watching, and I'll see you in the next video.